In this HVAC training video, I'm going over the initial electrical diagnosis steps for new service technicians that are working on a gas furnace that just doesn't seem to be turning on, or maybe the thermostat is blank, or it just doesn't seem to have power. And so I'm going over the step-by-step diagnosis to get that system back up and running. When you arrive at the job site and you notice that you have a blank thermostat and the building owner says they can't get the heat to turn on, nothing's happening, the very first thing you want to do is check the emergency switch. Make sure that's in the on position. Make sure that the breaker panel, breaker itself for this, which is 120 volt, typically it's a 15 amp breaker for an indoor gas furnace. Make sure that that's on. Also keep in mind that some thermostats are battery powered and not hardlined into the furnace, but in this case, it is powered directly from the furnace, and that's why it's blank. We're missing power, right? So the next thing that we're gonna do is we're gonna come into this sight glass right here and see if we see an LED that's lit, or see if there's an error code, some flashing that's occurring. If you don't see any light at all, then the thing that you need to do then is we're gonna remove this door, then we're gonna remove this door, and we're gonna move our diagnosis into this area right here. Now remember, when you come to the site, you're gonna have a top door and a bottom door. This bottom door on a gas furnace is going to have a door switch. And so that door switch needs to be shut. So during your diagnosis, like right now, the main power is coming in from the switch up above. It comes over to here, it gets broken, and then it comes over to power the circuit board, and out of the circuit board it goes to a 24 volt transformer inside. And so that's why when you're performing service, you typically are going to use a magnet. I don't like to use tape or anything like that that's going to come off, but you're acting as if this door is in place, and it's very important to remove this magnet after you're all done. We still notice that we don't have an LED status code light, which means we don't have 24 volt power for the status code. So next we're going to use a multimeter. So we have our multimeter turned on, and we have our display lit, and we're set to measure voltage for alternating current. And we're going to be measuring for electrical power, making it through this door switch. So we have the switch closed because we have a magnet in place. And so this is what the door switch looks like. And so with it closed, we should have power being able to go through. And we have one of our probes over here on the common neutral bar, and the other one we're going to place on one of the terminals of the switch between the spade connector and the switch itself. So we measure 0 volts there, and let's measure back here, and 0 volts there. So we don't even have power at this location. So now we need to backtrack and go back up to the main electrical switch for the furnace. At this location, we're going to have to remove the 2 screws and measure for power. Now we're going to place one of these probes on the ground because we can either put the probe here on the ground or the common in order to measure for voltage, and then the other probe, we're going to be very careful not to touch both the ground and the hot, but we're going to come back here close to the switch, and we're measuring 124 volts there. We're going to come down right along the plastic right there and measure at the other terminal, and we have 124 volts here, so we are losing our power between here and the door switch. And so we need to go ahead and see why, or where that's located at. So we remove this one screw from the top right here, and we're just going to turn this so we can see this. And we have turned the emergency power switch to the off position. And so basically our problem is between these 2 terminals and that switch over there in the front. And so this wire is good, and here's our issue. And so you can see that that connector broke apart, so we would have to cut this off and put a new connector in its place. But just say that wasn't the issue, say this door switch was the issue, that could be a problem. I want to point out that this right here a lot of times ends up having burnt contacts inside and fails. And so you can also check this with electrical resistance right across here. So say we wanted to check the integrity of this switch, we would turn our multimeter to electrical resistance, and that is the omega sign. Almost looks like an upside down horseshoe. And so we would check between these 2 points. And so you see that we're reading OL, that's open line. That means that the switch is open. And now I will close the door switch with my finger right here, and you see that we're measuring 0.0. So that tells you that we have a good switch, but we could end up having a bad switch where we have a very high electrical resistance across it, as if it's open even when it is closed. So that is something to keep an eye out for when you are diagnosing. I notice a lot of people end up using these little light switches for the gas furnace. Now these are 120 volt 15 amp rated, which is the same ratings of the furnace, but I highly recommend that you use these 120 volt 20 amp rated switches. They're going to last longer. They're going to have a tighter spring mechanism for when you are closing the switch, so when you are turning it on. And the thing with it is the contacts inside end up getting burnt on these little 15 amp light switches. And that's due to the high electrical current from the blower motor of the furnace. And so I find these failing a lot out in the field. You might not be able to see this little light down here, but the status code light is flashing very slowly, which means it's in normal operation, and that's based on the diagnostic fault codes for this furnace. And so when you have the door on here, it's going to be all dark, and you look through the sight glass and you're going to be able to see that status code light if everything is okay. So if that was not lit though, the next thing that you would want to do, if you know you have power over here at the door switch, so if we measure our power now, we should have 120 volts in, so we can put one on the common neutral bar and then one up here on the door switch, and you see we're measuring 126 volts. So we are good right there, right? So if you have voltage there, but you don't have a status code light, you know, the light is not being lit, you want to check for 24 volt power. So up here on the transformer, we're going to check the taps right here, and you see we have 28 volts. If you didn't have 28 volts, you can measure back here and see, do I have the high voltage power coming into this transformer? So right here, you see we have 124 volts. So if you had 124 volts here, but you did not have your, say, 24 volts, which is actually 28 volts, if you did not have that here, then that would mean that your transformer is bad. Now, if you still have 28 volts here and your status code light is not lit still, then you could have a bad 24 volt fuse. So once again, in this case, you can see that the LED status code light is flashing, and it's flashing slowly, indicating normal operation. And so the thing is, if it was not, it may be due to a bad 24 volt fuse. So you see the LED status code light is now not lit. Now, not all furnaces will have this occur. Some will show a status code error that says that the 3 amp fuse is blown. Hopefully you can see this, but the one on the left is good. The one on the right is bad. That's blown. It has that popped section in it. And so that could be the issue. And I have a whole nother video on finding low voltage shorts, because basically it's going to be one of these thermostat wires are connected to the ground accidentally, or they're connected to the common, and basically that has popped that that fuse. It could also be that there's, you know, a device that's shorted the ground, and so you have several different things that it could be. But this fuse is worth checking, and you just want to make sure to not just keep putting a new one in every single time and then having it blow. You know, during the troubleshooting, there's a way to just separate the wiring and things and measure electrical resistance until you figure out what the problem is. But check out our other videos in reference to that. So I just put our good fuse back in again, and make sure to replace a 3 amp with the same size. But you see our LED status code light is blinking again. And so if it was not and you had a good fuse, the next thing we want to do is just verify that we have power over at that fuse terminal. So say we did not have our status code light being lit, and we did have a good fuse, we would place our probes between our common and the one side of the fuse. We measure 28 volts. That's a potential difference in voltage between, say, this terminal here and this one here. Then we would measure over here. And so we're measuring both sides of the fuse. We measure 28 volts, and we know that our fuse is intact because of that. And so if our board still did not have the LED status code light being lit, then it's very likely that the board is the problem. However, there might be some boards where the 24 volt power coming in has to go through some of the safety switches, but that's usually not the case, because when a safety switch trips, like a low voltage 24 volt safety switch that's between, say, 24 and 29.5 volts, what happens is this status light right here is going to blink a specific code when one of those switches is tripped. I'll give you an instance of what that looks like. That right there is the flame rollout switch. And that is a very important safety switch. And so it protects against potentially flames popping out from that combustion chamber. And so what's happened now is you have the blower motor running and the inducer motor running, and it's not going to allow ignition to occur even if there is a signal for heat to turn on. Now we're going to move on to another scenario. So let's start our diagnosis again, and in this case you see that our thermostat once again is blank, and we want to move down to the sight glass as the next step, and we want to see if we see the status code light, and in this case you see it's blinking very slowly like normal, but we don't have power to the thermostat. So we know we have 120 volts, we know we have 24 volts, and so we can start our diagnosis right over here at the thermostat subbase. So we need to remove this front cover. You can see our thermostat is blank, and so we need to take off the face, and we're going to locate two terminals. One's going to be the R terminal and one's going to be the C terminal. And so you also notice, hopefully you can see that the R to RC has a little jumper there, and so we've got a red wire attached to the RC and we've got a blue wire attached to the C. So we're going to be measuring for 24 volts between the R and the C. So it doesn't matter whether we put this left-hand probe in the RC or the R, because there's a jumper, and so we need to have 24 volt power here in order to power the thermostat, and you see that we have none. We've got 0 volts there, and so that's the issue. Now what happens when you turn heat on is you're going to have the R terminal and the W terminal are going to touch. That's what's happening. Anytime that you have the thermostat calling for the sequence of operation for heat to turn on. And so for this thermostat to even do that action, it needs either 24 volt power, or in this case, it could also use batteries, but these batteries look like they're dead because the thermostat face is not turning on. So let's turn our multimeter light back on. We're gonna change our setting to volts for direct current, and we're gonna measure between these batteries right here. So if we go from here to here, you see we're measuring 1.9 volts. Well, the thing is, these batteries should be measuring at least 1.5 volts apiece. And the reality of it is, if they're new, they're going to be about 1.65. So 1.65 times 2 is 3.3 volts, and we don't have anything near that. We've got 1.9 volts, which means they're completely drained. So as these batteries are used up, the voltage lessens until basically it does not have enough power in order to turn the thermostat on. That's going to be our issue. Now, even if we did have good batteries here, the thermostat would turn on, but the issue is, you did notice earlier I jumped between R and W and nothing happened inside the furnace. And so there must be some other issue besides maybe a problem with our common wire. And so we need to diagnose down in the blower compartment. We're back down in the blower compartment, and you can see the LED status code light is blinking like normal. That's because our door switch is shut, and we reset the multimeter to measure voltage for alternating current. And so we're going to put one probe on the R terminal and one on the C terminal. And so we're measuring for 24 volts, so that's anywhere between 24 to 29.5 volts, and we're measuring 28 volts. So you can tell that this wire right here, your red wire, somewhere between here and the thermostat, that wire is broken. And I'm going to get to that in a second. So you see that we have this wire bundle right here is going to your thermostat. And this red wire is leading to a yellow wire. So these two wires are leading to 3 condensate safety switches that are wired in series. And so one of those must be broken. So if we measured up inside this wire nut here to common, you can tell that our power is being broken in those switches somewhere. So we got 28 volts there. Now let me also just show you, you could also take a probe on the ground from R to ground and you'll have 28 volts. So if you need to, and you're kind of jumping around across switches or something like that, you can just place your one probe on the ground and then use your other probe to measure across switches. I just want to quickly show you that we can get the fan to turn on If we jump from R, which is right here, to G, that's always your indication for your fan to turn on when you have 24-volt power to the G terminal. So we lost our 24-volt power, right? Because we disconnected. Now let's go from our red to W. So that's going to start the inducer motor, which is the sequence of operation for heat. So you can tell our furnace is not having any problems. It's just our thermostat wire to the thermostat itself that has an issue. So let me show you what those switches look like. So starting right here in this blower compartment, you see that we have 3 wire nuts. So there's 3 separate switches that are wired in series. It's going through all 3 of those and then back over to that terminal on the R of the circuit board. So what we have here is a float switch for the condensate pan, and so that's located right here. And so if we were to take this out, you can see that there's a float inside, and so that could be the issue. Over here is a condensate pump. So that has an internal float. You can see that the alarm is not being lit right now, so doesn't seem to be an issue there, but we're going to check it with the multimeter. And then up top, there's an additional safety switch, and that is in the secondary port of the drain pan. And so that's located right there. Now we're going to measure for voltage, so we're going to put one probe on the common, or even the ground for that matter, and we're going to put the other probe into this wire nut, and we see that we measure 0 volts still. So that's telling us that the switch that's connected to these black wires is the problem. Now, we may have an additional problem once we fix that on one of the other switches as well, but since this wire is the one that's going into the R, it's going through this black wire into the switch and then out of the switch and over to here. So we should have 24-volt power just like we have when we measure between here and here. So we have 28 volts right now. And so let me show you what that switch looks like. Those black wires are leading to this safety switch, which was mounted in the secondary part of the condensate drain. And of course that would normally be glued in, but just for example, I wanted to show you this. So if that coil and drain line was clogged, what's going to happen is this float is going to be in the upwards position, just like I have basically tricked out right now. So when that falls down, we should now have power at that wire nut. So we're going to go ahead and test it again. So you see we're measuring 28 volts now, and so we are good now. Once again, if I just put the probe on the common, 28 volts, 27.99, and then let's measure through this switch right here. So that one's really tight. Sometimes you have to find a really good spot inside to make contact with the metal. That one's good, 28 volts there. 28 volts there. So now we should have power up at the thermostat. Now remember that safety switch right here is a protection device to make sure that you don't have the condensate overfilling over the condensate pan due to a clog, which would basically create a lot of water damage within the furnace itself and within the building structure. So you want to make sure to clean out that condensate line properly. And so once again, all these PVC fittings, they should be primed and glued while they're dry and have a chance to set before you go ahead and turn, say, an air conditioning system on to run it. Now we're going to check for 24-volt power between the R and the C terminal. And you see we're measuring just under 28 volts. And so we can remove our multimeter and put our thermostat on, and it should now light up. What we're going to do is I'm going to show you the sequence of operation, and what's happening inside this thermostat is the red and the white wires are touching. That's the R and the W wires when you turn heat on. So we're going to go ahead and turn heat on, make sure that it's set to a high enough temperature. And the very first thing that turns on is this inducer motor. This pressure switch is confirming that that inducer motor is working. And if you can see inside of here, there's a hot surface igniter, and that's turning cherry red. And so after that gets very cherry red, we're going to have the full gas flow going into the burner area, and so you're going to have ignition. Over here on the purple wire, you have the flame rod, and that's proving that you have a flame. And then you come down to this circuit board down here, and the circuit board is understanding that the flame is there and it has a blower on delay, which means that the heat exchanger needs to warm up before the blower motor is going to turn on and circulate that hot air through the building. And so we're in that initial maybe 20 seconds, 30 seconds, and now the blower motor has turned on. I hope this video on electrical diagnosis has helped, and if you want to learn about how to solve intermittent problems or inducer motor issues, or how to troubleshoot a pressure switch or thermostat wiring, make sure to check out some of the other videos we have linked down in the description section below. And if you want to learn more about HVAC, head on over to acservicetech.com. We've also got our books there, and we have a bunch of free resources such as articles, quick tips, calculators. And so our second edition book is there, which addresses all the procedures that you really want to know out in the field in regards to refrigerants. And it covers the new A2L refrigerants. And if you're lost on mini splits, this is going to give you a good foundation so that you can also install and service inverter mini split systems. So we've got the full outline to both of these books over at our website over at acservicetech.com, and they're also available over on Amazon and at True Tech Tools. Hope you enjoyed yourself. We'll see you next time at AC Service Tech channel.